Alright, for the first topic for this review from Chem 351. 351 review. One of my favorites, hybridization states. Now, super important for understanding reactivity, which we'll talk a lot about this semester. There's three types of hybridization states. There's sp3 hybridized, sp2 hybridized, and sp hybridized. Those three types of hybridization states have different types of molecular orbitals associated with them. For sp3, it's sp3, 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 and sp3. For sp2, there's a p orbital now and 3 sp2s. Notice there's always 4 of these. Right. Sp has 2 p orbitals and then 2 sp orbitals. Example of an sp3 hybridized atom is just simply a carbon. No pi bonds with that carbon. An sp2 would be an alkene with 1 pi bond. Pi bonds are formed from p orbitals. An example of sp hybridized would be an alkyne, which of course has 2 pi bonds, which means it must have 2 p orbitals. Only p orbitals form pi bonds. Another important aspect of hybridization states is actually being able to draw these, so in the actual molecular orbitals. So for sp3 hybridized, geometry is tetrahedral. Bond angles are 109.5. And the way we look at the orbitals, all the orbitals are essentially the same. They're all sp3 orbitals. They're the best at drawing, but there they are. The way we think about this is that all these orbitals have to be the same because the bond strengths have to be the same. The orbital overlap has to be the same. With something like methane with 4 hydrogens. For something like that's sp2 hybridized, it's a little different. It's trigonoplanar. Bond angles are 120 degrees. We now have a pi bond. So that means we have a p orbital and sp2 orbitals. Which means these have less p character versus sp3 up here, which have 75% p, 25% s. These sp2s are 66% p, 33% s. And the way these will look is you'll see the p orbital. The pi bond is shown here. That's an example of an sp2 hybridized. Sp hybridized is linear geometry, 180 degrees bond angle. It has 2 p orbitals. And now 2 sp orbitals, which are 50% s, 50% p. So a more rounded shape. They'll look like this. It's one of the p orbitals. The other p orbital is at a 90-degree angle away from that one. And then finally there's this sp bond there. That's the geometry of an sp hybridized alkyne, sp hybridized carbon or atom. We should also look at two other examples to make sure we understand this, is whether or not carbocations and carbanions, what their hybridization states are. So carbocations are sp2 hybridized, while carbanions are sp3. If we look at the molecular orbital picture, we'll see why that is. If the p orbital is empty, we want this empty p orbital to be as close as possible to these electrons here. That's at 90 degrees. That makes it as close as possible. Right, opposites attract. However, for a carbanion, it's just the opposite. Now we have a negative charge in the orbital. And to get these things as far away as possible, we want sp3 hybridized, because this bond angle is 109.5, as far away as possible, which is better. So another thing I wanted to go over was, from the first semester, was identifying acids, bases, and nucleophiles and electrophiles. For acids and bases, acids will traditionally have a weak CH bond. So a way to think about an acid is to find where there's weak bonds to hydrogen. So for instance, a carboxylic acid has a polar covalent bond between O and H. In comparison, just an alcohol is not as good of an acid because there's this resonance pull when you look at the conjugate base. Right, so this is more of a base than this. However, then if you extend it a little further, so now what if I change it to NH2? Now we got to look at, instead of looking at here, we looked at resonance structures, right? Delocalized versus localized. Now we compare electronegativity. Oxygen's more electronegative than nitrogen. That means nitrogen is more likely to act like a base, right? That means the OH bond is a weaker bond, right? So comparing these two, OH is more likely to be an acid, and this is more likely to be a base. More polar bond, electron lone pair is more likely to be reactive because it's also less electronegative. The same thing holds true, the same idea here if we talk about electrophiles and nucleophiles. An amine is more likely to be a nucleophile than an oxygen because of electronegativity. Right? If something's wrapped up in resonance, it's less likely to be a good nucleophile as well. It's more stable. Another examples, a couple examples would be we've seen. So if we pointed an arrow at specific carbons, or other bonds, we'd say here this arrow is pointed at a delta plus carbon, that would be considered a electrophile. Pointing at the oxygen, that would be considered a nucleophile. The carbon bond to fluorine or anything else that's electronegative, that would be considered an electrophile. And the hydrogen bonded to a nitrogen, which is more electronegative, that would be considered an electrophile as well. So you really got to ask yourself, who has the electrons in the bond? And that tells you, if it has the electrons, it's a nucleophile. If it doesn't have the electrons, it's the electrophile. Next thing we're going to talk about is an NMR type problem. Basically, the first thing you got to remember for NMR is just the four things that it tells us. The first thing it tells us is the number of types of chemically non-equivalent H's. And it tells us different number of types of H's it has. The second thing it tells us the relative number of those H's. In the molecule. The third thing it tells us is something about where the frequency that the peak is at, which has to do with shielding or deshielding. If you're shielded by electron density, you're farther upfield. If you're deshielded, you're downfield. And finally, the fourth thing it gives us is something about splitting, which helps us understand what hydrogens are next to each other. Usually 3 bonds away. And we see this with coupling constants. So now to bring those 4 rules together, let's look at an example. An example would be, let's look at a benzene ring with an alcohol on it. Actually, I'll make that an ether, why not? The first thing we need to do is identify the number of hydrogens. That was the first rule. So the first thing we would do is identify the number of hydrogens. So I like to draw in the hydrogens, usually that helps. Now from here we need to identify different ones. So these 3 are all the same. We can label those A. Looks like these 2 are the same. We'll label them B. These 2 are the same as C. These 2, since this is symmetrical, are C. These 2 will be D, and this will be E. Now, this is easy for me to do at this point. This takes practice. This takes lots of practice to see which ones are different. Make sure you work on finding out and practicing the number of hydrogens. Alright, so how many do we have here? I have my count 1, 2, 3, 4, 5, 6. So we'd expect, so there's 6 types of H's. So we'd expect 6 peaks. Now the relative number tells us something about the molecule, the relative number to each other. So for A, there's always going to be, if I did A, B, C, D, and E, and looked at the relative numbers, relatively A always has 3, while B will always have 2, C will have 2, I did C twice, my bad. To back up here. So this one I'll make F. So D will always have, C will have 2, D will always have 2. E will have 1 and F will always have 2. Yes. That tells us that is found from the area under the peaks. Right, the integration. The third thing we'll look at is now we're trying to figure out where these things are at as far as shielded or deshielded. So we gotta look at where they're by the electrons. So I won't draw the spectrum, but just simply looking at it, if you're closer to a more electronegative atom, that makes you more deshielded because the electrons aren't shielding you. So in this case, I would say A and B are going to be the most deshielded. Because they're near oxygen. C will be less. Now for E, F, and D, those are aromatic. So they're actually much farther downfield than normal. Around 7 ppm. These would be around 3 or 4. And then this one, since it's benzoic, would be around 2 ppm. So the final piece here is the splitting. Alright, so you gotta go through and find the nearest neighbors. A will be a singlet. There's no nearest neighbors. B will be a triplet. Has 2 nearest neighbors in C, the n+1 rule. C will also be a triplet and share the same coupling constant. It says it's coupled to B. F will be coupled to D, and that will be a doublet. D will be a doublet of doublets or triplet. You want to look at it. And E will also be a doublet. And if they're coupled to each other 3 bonds away, that means they're the same coupling constant. And that's how we know they're coupled to each other. Now we're going to do some chair drawing practice. So of course, to draw a chair, we draw 2 parallel lines. Then draw 2 more parallel lines. And yet again 2 more parallel lines. And if we draw them the other way, we can do the same exact thing. You get the other chair conformation. Chairs have 2 different positions on each carbon. They have the axial position and the equatorial position. And it goes every other one. Axial down, equatorial up. Axial up, equatorial down. Axial down, equatorial up. Axial up, equatorial down. Axial down, and then equatorial up. So on and so forth. So you can go axial up, equatorial down, over and over again throughout the whole ring. Now the other thing we want to think about is this ring flip. Right, so the other ring has the exact same positions. I'm going to number these carbons now. 1, 2, 3, 4, 5, and 6. We want to trace where those carbons will be at in the other chair conformation once we do a ring flip. So what's going to happen is carbon 4 is going to be pulled up, and carbon 1 is going to be pulled down. So carbon 4 is actually going to be here. This will be 5. This will be 6. 1 got pulled down. 2 and 3. Now the interesting part about this is where if I drew a ring, a 6-membered ring, and said this is Y is pointing up and X is pointing down. Y will always be pointing up and X will always be pointing down. Now Y will not always be equatorial axial though. It'll either be not always be axial. As long as it's going to be pointing up. So let's say if carbon 1 was Y, had Y and X on it. In this chair conformation, Y, let's say Y is pointing up, while X is pointing down. Y is in an axial position here, Oops, Y is in an axial position here, and X is an equatorial position going down. Now, if we go to, after the ring flip, the up position is now equatorial, and the down position is now axial. So X will be in the axial position pointing down, and Y will be in the equatorial position pointing up. That's the biggest change in the ring flip. No bonds are broken, and you're still on either the top or the bottom side of the ring, but whether you're axial or equatorial will change. One mechanism that really stuck out with me that people were having quite a bit of trouble with was the bromonium ion. I just want to show an example of that to make sure we understand what's going on in this reaction. Essentially, we take an alkene, we react it with Br2. So the first step, the pi bond is attacking the bromine. The bromine bond breaks. Then the bromine also comes back here and attacks the pi bond. 3 arrows, 1 step, no carbocation intermediates. No carbocation intermediates. The addition is also cis. So when you form this bromonium ion, the Br is on one side of the ring. It also could have been on the other side of the ring. There's no preference. One side or the other, because this is sp2 hybridized and it's flat. The second step is the Br attacks from the back side on the opposite face where the sigma star is at. And the final product then, the bromines end up trans to each other. No carbocations, no rearrangements are taking place. Another caveat of this, if we had to think about, was also if this alkene was substituted, the more substituted the carbon, the more likely to be attacked by the bromine. Biggest point, 3-step first mechanism, no carbocation intermediates, and trans products. Okay, I want to look at a free energy diagram and the possibility of forming 2 products from a reaction. So if we look at this, let's say we have the same starting materials, and we can form one of 2 products. Product B and product A. B is more stable than A. Now, thermodynamics looks at products. How much? How stable are the products? So in this case, B would be a thermodynamic product because it's more stable. So more likely to form that. However, if we start taking a look at the actual free energy diagram and actually the transition states, that might not always be the case. So for instance, for B, it might take a great deal of energy to get to the transition state to form B. Whereas with A, it might take less energy. Kinetics asks how fast. So it looks at the transition state energy. So lower transition state energy means it would form faster. So in this case, A would be a kinetic product because its transition state was lower in energy, so it would form faster. Whereas B would be the thermodynamic product because it's more stable. These ideas will become important later on, and obviously we continue to talk about these, about how much and how fast things are forming. Another thing we should take a look at is our R and S practice. R is clockwise, S is counterclockwise. So if we look at something, let's draw. And these are only pertinent for sp3 hybridized atoms, or carbons usually, with 4 different things bound to it. They have 4 different things bound to it. So if we look here and say H, we put a bromine, put an iodine, we put an OH. First thing we need to do is recognize, are there 4 different things? In this case, there's 4 different things. Then we need to rank these 4 different things. Usually it's easiest to go from highest to lowest. Lowest is carbon. This is based on atomic number. Highest would be iodine, so that'd be 1. Then bromine, and then oxygen. Now if you have your model kit, your red, white, and blue model kit, that would be key here. So we usually say red was ranked 1, blue was 2, or white was 2, blue was 3, and then green or whatever other color was the 4th one. So you want to grab that and rank those. And in this case, this will be R. And so if it rotates clockwise, it's R. Counterclockwise is S. You could draw its enantiomer. Right? Its enantiomer would of course be its mirror image. So in this case, if I switched Br here and put the H here and put iodine there, put OH here, let's see what this one ends up being. We do our rankings again. This is 4, this is 1, 2, and 3. So in this case, it would actually be S. So make sure you practice these and work on these rankings. Alright, the final piece I want to look at was something called Newman Projections. Alright, Newman Projections was another way to look at a molecule that has stereochemistry or has wedges and hatches. Usually they look like these sawhorses. You'll see something like this, with maybe H here, CH3 here, say an iodine, a bromine, and another H. What we'll want to do is basically take your eyeball and pretend you're looking down this. So to do that, we draw a circle. And in this case, if this is carbon 1 and carbon 2, carbon 1's at the front. And we can see the bromines pointed out, right? And these other ones are pointed down. So we take our Newman projection like this, and we'd look, we'd see the iodine here sticking out at us. So here it would be right here. The bromine is going back, so that'd be here if I turn this. Here is the H. Now if we go to the next carbon over, you can see the H is pointing out at us on the same side as the iodine, so that means it would be over here. So here's where the H is at. The CH3 is at the top. That leaves the OH in this position. All right. Make sure you practice doing some Newman projections as well.